if you make an overall proposal to account for how things are currently, as I say, you want to usually operate within the principle that it should be as simple as possible. You have argued, well, it is quite simple. I think the Occam's razor principle is you don't generate entities unnecessarily, and an infinite number of universes just breaks that principle coaching horses. But the other people have said, well, if you are proposing something as an explanation of what there is here, but you have no evidence for it, what difference is there between a multiverse proposal and the traditional religious proposal of God, which you say, well, we can't explain everything here. We're going to propose that it's all made by something else, namely God. Isn't the idea that everything here comes from the multiverse really just a scientific version of theology?
No, I don't think so, because every time someone makes a theological statement, it stands on its own merits or whatever forever, because there's no experimental evidence supporting it. It's just pure conjecture. But as I mentioned, there are at least 4 major ways in which to verify the theory. And each one gets us closer to a complete verification of the theory, not one experiment that clinches it all at once. There's no smoking gun. But the same thing with the Big Bang Theory. There was no smoking gun for the Big Bang Theory for many decades. And so now what I'm saying is it gets us closer to truth. But religion does not get us closer to truth. It's the same. Arguments made thousands of years ago are identical to arguments that will be made thousands of years from now in religion.
Do you think, Roger, that one of the reasons that the multiverse in the version that Michio is putting forward has been proposed is because of the concern that quantum mechanics has built into it an uncertainty which Einstein was certainly uncomfortable with, and it's somehow trying to get rid of the unknownness in quantum mechanics and to say, well, we're just going to generate entities for every bit so that it's no longer unknown.
Well, if that's what it's doing, it's not very impressive. I mean, quantum mechanics has a problem, and I think that's true, despite it being the most wonderful theory we've ever had or something. It has a deep problem, but I don't quite see why that has anything to do with this multiverse issue, which has to do with string theory. I mean, there seems to be a big confusion about different concepts, different problems that people have, and calling them all the multiverse or something. I don't quite see it solves any of them, actually. I mean, Maxwell's equations have lots of solutions. Yeah, of course they do. So do Einstein's equations, so do Newton's equations. Why does that drive us in the direction of a multiverse? I just haven't got that argument at all.
And what do you think, what is driving that? I mean, it's very popular, isn't it? It sells books, sells theories, it drives science fiction. What is it about the idea of, another universe to this one that we found so appealing?
I have no idea. I don't find it appealing. Yes.
So maybe if I could say something about it, I think it depends on what we mean by popular. It's arguably popular in the popular science sense. You read popular science articles about it, people write books about it, and those books sell very well. We go to festivals and people talk about it, right? But if you look at what's actually happening in the community, in physics, there are very, very few people working on it. It's interesting brain gymnastics. I like thinking about the possibility that there are infinitely many copies of me out there somewhere in the universe, and they're living their lives in other ways.
So far, the multiverse theory as applied to quantum mechanics, which is many worlds theory, agrees with all the data. In fact, there's no way to differentiate the Copenhagen interpretation from the many worlds interpretation. They are identical with regards to experimental verification. So you don't have to believe in the multiverse theory to be a quantum mechanical physicist, because the data from the many worlds theory and the data from the Copenhagen interpretation are identical. But when you start to talk about cosmology, and you start to talk about the universe, where it all came from, then you start to ask these philosophical questions about where did the universe come from? Is there another copy of me in another universe someplace? That's what resonates with the audience, I think, because people wonder about these things. There's a poem by Robert Frost, the road not taken. And you always wonder what would have happened if I took that other road with a fork in the road. This is an internal question. And that's why it resonates with Hollywood, because now we have at least a physical theory which entertains the concept that yes, there are many roads to reality.
Are we always going to be in a situation where our broadest accounts of the universe have elements which are untestable?
Well, I think untestable, but in principle untestable, or just we don't have enough energy or enough money or something like that. I mean, a lot of things haven't been tested because they're pretty difficult to do. An example of that is the issue of the reduction of the state in quantum mechanics, or the collapse of the wave function. Of course, you have to have a good alternative theory of at what level do you expect to see that. And there are experiments which are proposed at the moment, some which have been performed and haven't quite got there. Maybe it'll take a long time. But these are honest experiments which will show, if they come out the way I expect, actually, that there is something not quite right about quantum mechanics, and that you don't have all these other universes existing and so on. It's one thing happens. And that thing happens in a certain lifetime, which you can get a good estimate for, according to some of these schemes. And it seems to me that's the way science progresses. I mean, you suggest experiments, and some of them are quite expensive, and so it takes a long time for people to get around to doing them, or they may be technically very difficult, such as the ones I'm talking about here. But does that, would this be considered to be arguments against multiverses? I mean, suppose now a very good experiment comes up which shows that a quantum superposition does become one or the other in a certain lifetime, which maybe is predicted. Now, does that say, oh, well, we don't have to talk about multiverses anymore? Or is it really a completely different argument that's being presented here? I just feel that there's too much fuzziness, too much, well, particularly the arguments from string theory, which I don't really see.
I suppose I was wanting to ask a more general question. Is there something about the way that we put our theories together which means that there is always an element of untestability somewhere? So that, as an example of the sort of thing, I mean, so Heisenberg can certainly be interpreted as advocating the view that physics is not uncovering reality, and that's because it can't do so in at some level. There's some residual element which is about the limitation of being human and making observations would mean that we can't get through to it. Another way of thinking about it would be, you know, are there elements of science, for example, the notion that the universe is governed by laws, which is an essential idea to science, but you know, can we really test the idea that the universe is governed by laws? Is there something that, you know, and are there therefore some essential assumptions, as it were, in any theory that we can't get at?
Well, I mean, you might say tomorrow the laws are all changed, and I mean, that could happen. I don't expect it to, but I can't quite see. I mean, all the observations that have been made up to date, I mean, they tell us that the world has to be according to the physics that we understand now. I mean, just that it seems to work pretty well, and very well under certain circumstances. And, I mean, take general relativity, it's now extraordinarily well tested. I mean, things like a clock down here runs at a different rate from a clock up here. Well, you know, it used to be this tower, and now it's from here to about there.
Sure.
I mean, these things are confirmed. These are really precise things that theory says, and experiments can be done, and they say, yes, this theory agrees with what we observe. Now, string theory is nothing like that. And in these postulated ideas about other universes around, there's nothing like that. So I can't quite see why we should consider those ideas as comparable with these wonderful things we do get from the physics we know.
So we have no telling that the laws of nature will still work tomorrow. This is just something which underlies the entire scientific methodology, that we just assume to be true, but we can't test it itself, because how would we test it?
Yeah,
right?
exactly.
But there is a somewhat more innocent example of something that we can't test, which is anything that is too rare to happen in the time that we measure it. Which an example may be proton decay, which is something that we've looked for a long time, but we still haven't seen a single proton decaying. But there are also other things, like, for example, the cosmological constant may not actually be exactly constant. It may very, very slowly change in a couple of billion years, but we'd never be able to test it. And that's an interesting example, I think, because what the cosmological constant does eventually determines the ultimate fate of our universe.
Is there a place for proposing theories that we don't have evidence for, or that perhaps we can't have evidence for, but which somehow do function to hold our overall account of the world together in some way? Is there some purpose in that exercise, even if we think, well, actually, this isn't really science, it's something else?
I think there is a purpose in that. I think it's worth thinking. Certainly, if you can have a scheme which is simpler in some respect, and it may not be testable, but on the other hand, it gives you an overall picture which is simpler than one which is different, but still not testably different. So it's certainly worth thinking about such things. But I think that it's really going over the top when one's talking about these multiverse ideas, which partly come from things about quantum mechanics which I think aren't correct, and someday we will, I hope, see what should replace them. But I can't quite see why we should be driven into this idea of all these universes coexisting. That I haven't understood.
So Michio, do you think there will always be a remainder of topics that we are not able to explain, which are untestable at some level?
Yes, there is a point at which all the known laws of physics collapse completely, and that's the Planck energy. The Planck energy is 10 to the 19 billion electron volts. That is a quadrillion times more powerful than our most powerful machine, the Large Hadron Collider. It is the point at which black holes and big bangs, all of that stuff takes place in the realm of the Planck energy, where Einstein's equations become useless. Einstein's equations diverge completely at the Planck energy. The laws of quantum mechanics, you have to have higher loop diagrams to control the divergences. It's a real mess. But that is the energy of the center of a black hole. That is the energy of the Big Bang. The most interesting places in the universe are beyond our mathematical ability because they exist at the Planck energy. In fact, the only theory which can operate at the Planck energy is string theory, but that's a whole other question. But the question you ask is there a point where the laws of physics as we know them break down? And the answer is yes. Two places, the center of a black hole and the beginning of the universe. That's where the Planck energy starts to come in. Wormholes dominate, all sorts of crazy things begin to happen. We have to think about the possibility of time travel, of gateways of the universes. It becomes a real mess at the Planck energy.
Yes, well, obviously the question is whether we take those descriptions seriously, isn't it?
No, I don't think we need to. No, I mean, the Big Bang is, well, I don't want to go into this, because the Big Bang is a different story from the singularities in black holes. They're a completely different story. And to try and apply the same arguments to both is, in my view, quite wrong. I mean, I had the wrong view myself for a long time. So there's nothing against contemplating these things. I just happen to think, for what I regard as good reasons, that the singularity in the Big Bang is of an utterly different nature from the singularities in black holes. And this difference is extremely important. It leads to the second law of thermodynamics. It's part of the story. If they weren't different, we wouldn't have a second law of thermodynamics. I mean, these are things in physics that we see, very blatant things in physics, which if you trace them back, lead us to the conclusion that what goes at the Big Bang is utterly different from the singularities in black holes. And therefore, to put them in the same category and saying string theory or multiverses or something is going to resolve that, I can't see that at all.